Hello and welcome to another episode of the Measurement Lab. I'm your host, Elijah Carey, and today we're going to be taking a deep dive into real time. So I'm joined by Ken Sharp. Ken, introduce yourself and give us a little bit of your background with LabVIEW and LabVIEW Real Time.
Yeah. Hi. So my name is Ken, and I have been on the LabVIEW team for just over 20 years now. And most of that time has been working on the LabVIEW real-time product.
So what was your first version then?
7.0,
Okay, so
which
you would have,
I'm trying to figure out what year that was. Like I'm not, it's probably like 2004, 2005, something like that, I
I'm
think.
sure people watching will readily comment below. But yeah, that sounds about right. I joined in 2005 when we just launched 8.0, so it would have been before then, a few years before then. But at the time, real time would have been relatively new, having been around for a few releases, and you've been working on it basically ever since then. But for the uninitiated, maybe give us a little bit of an overview of what it is when we say real time and why it's different.
Yeah. Well, so the first thing is that real time part. So what that means for us is it's not that your LabVIEW code will run faster, it's that it will run more deterministically. So that just means, when you're running a loop, um, the time between loop iterations will stay as constant as possible given, the operating system details.
Yeah, and this was something I know when I first joined NI and heard about real time. Didn't fully understand or appreciate the value of. So when thinking about determinism and related concepts like jitter, what are what makes it hard? Let's understand the problem space first. Like why isn't our typical laptop or computer, which we think of as pretty performant, when is it insufficient in terms of its deterministic behavior?
Yeah, well, it's really the complexity of modern operating systems that make that really hard. So because they're doing, 100 or 1,000 different things in the background that you're not seeing, that means that running something that requires those CPU cycles and to be really reliable is hard because you're moving your mouse or you've got a browser tab open or whatever that's using up CPU cycles. And so kind of managing all that from an operating system standpoint is hard. And really modern operating systems aren't optimized to do this kind of real-time processing. They're really meant for either servers or just desktop users where if you have milliseconds of delay or latency between different things running on the CPU, that's okay. But when you're controlling machine or monitoring some sensors or things like that, that really makes a big difference, those milliseconds. So the real time part of that is trying to trim down the milliseconds down into more like something like microseconds of jitter or latency, whatever you want to call it.
So how do you measure determinism? How do you evaluate how deterministic a system is?
Yeah, well, you can measure it by basically taking looking at a clock on the computer, and a clock meaning something that's just um, ticking at a given clock rate reliably, and you can kind of compare your execution times and basically how long you spent not executing and how long you spent executing and things like that. And that's how you can kind of measure those numbers of how long each iteration of your application is taking, and also how long it takes before your application comes back and is executing again on the CPU. So that's really kind of how we measure that.
So is there a threshold at which there's it's not to say that a desktop operating system like Windows, Mac, or Linux isn't deterministic. It is how is it the window of time in which you guarantee a certain action is performed. Is there a threshold at which you would assert, like, once you're past this level of requirement for determinism, you really need to move away from your typical host operating system?
Yeah, I mean there's no definitive answer to that. It really depends on the application itself. But I think just experience has said a normal desktop application, you're going to be talking in the milliseconds or tens of milliseconds would be your general kind of determinism or maximum determinism uh, number. And for a tuned real-time operating system, you can get it down into more like tens of microseconds. So like about 1,000x improvement in that kind of maximum latency or determinism number. So that's
So,
just kind of a rule of thumb. It varies greatly
okay.
depending on hardware and application, things like that.
Yeah, what else you're asking the system to do.
Right.
So is it we've already, dove deep on just determinism. Is it all about determinism? Or are there other reasons and use cases where real time is a preferred choice? Yeah.
Yeah. Well, I think the larger kind of ecosystem is like LabVIEW real time is really good for designing embedded systems. So just putting aside the determinism aspect that we were talking about, embedded systems are really meant to be those the like usually headless systems that are just running some important process without human intervention. So LabVIEW Realtime, in addition to the determinism features, also allows you to run LabVIEW code remotely on targets that are on the network, but you might not have right next to you. So that kind of you know it gives you a lot of flexibility as far as uh, designing embedded systems and that kind of thing.
So as I mentioned earlier, I think of I think of the big operating systems as obviously Windows, Mac, and Linux.
Mhm.
And so when it comes to a real-time target, it's kind of a different portfolio of operating systems. So what operating system do we I know we've used historically some different ones. So what do we use these days and what makes that operating system uniquely capable of being used in a real-time system?
Yeah. So yeah, we've evolved over the years, but now our real-time targets all use uh, Linux under the hood. So we're using um, features of the Linux kernel called preempt RT, which is really just it's a set of features in the kernel that basically give you more flexibility and are optimized for that kind of determinism and minimizing latency for processes. So we run LabVIEW on a Linux operating system that's tuned for real time performance.
And I believe we actively contribute. I mean, this is a version of the Linux kernel that exists, but I think we're a pretty active contributor to it, right? Can you set the record straight on that?
Yeah, yeah, absolutely. So yeah, we're definitely kind of members of the Linux community. So we've contributed patches to the Linux kernel, and definitely we strive to kind of keep our kernel up to date with the latest and greatest kind of features that the Linux community is creating. So yeah, we're very active participants in that community.
Okay, so we had a previous episode with Greg Richardson talking about the compile chain and what happens under the hood. If you haven't seen it, you should check it out. But he explained how we transitioned from our graphical code to ultimately defer and LLVM. Obviously, if we're talking about a different execution target, something about that is different. My code looks the same. Where in that process do things diverge when you're talking to a real time system?
Yeah, absolutely. So yeah, we do. It still uses the same kind of compiler technology that Greg talked about in that previous episode, but we do slightly different. We cross compile the code. So basically, what happens is when you hit the run button on a VI and it's targeted to a LabVIEW RT target, we will go query the target and say, okay, what type of CPU are you running? What CPU architecture are you running? And it will come back and say ARM or Intel or whatever the case may be, and then we will use that information to compile your LabVIEW VIs for that CPU before sending them over to execute on the target. So that's kind of where it diverges is we could be compiling for something that is not the same as the desktop uh, instance of LabVIEW that you're you're using.
And since you mentioned ARM and other execution targets, what are the execution targets we're currently supporting on real-time
Yeah, so,
systems?
so we have 32-bit ARM, and then we also have 64-bit Intel CPUs. So those are the current setup targets, are all those two architectures.
Okay, so and now ultimately, as we talked about earlier, one of the big use cases is determinism, which, just to emphasize, when I say something needs to happen, I have some level of assurance it'll happen within a specified window. But we don't control what users do in their code, and there's nothing stopping them from putting a 10-second wait function somewhere in a LabVIEW block diagram. So, what are some of the best practices for ensuring that the processes that need to respond in a deterministic window perform as they are expected to?
Yeah, it's definitely there's some best practices there. I think kind of the most important thing is to try and keep things in separate loops that are using hardware, and that could even be accessing the network or actually taking a measurement from a device or what have you. And so uh, if you can kind of keep those in different loops, even using timed loops is a really good practice for that. That's a good way to prevent kind of a network access or something from hanging up a loop where you need it to respond quickly and deterministically.
So you said something. Let's go back to it. Timed loops, right? That's a concept that's unique to real time. Correct me if I'm wrong. What is it? What does it do?
Yeah, you can actually use them on Windows, but they are more performant and tuned for the real-time use case. So yeah, it's basically the idea behind it is um, it's like a really souped up while loop. So um, it looks similar on the diagram to a while loop that you may be familiar with, but it has some more configuration that you can do on it. So you can specify different timing sources. On real-time targets, you can use a kilohertz or a megahertz clock. You can even use timing sources that are based on data acquisition devices, for instance. And so you can specify that. You can configure what rate the time loop should run at. And then within the time loop, you can even get feedback. So it's measuring how long it takes each iteration to run, for instance, and you can get various kind of statistics basically on that time loop instance. Like if it took longer to run than you thought it would, you can get some feedback in real time
So
as the code is executing.
so if I specify a time loop should execute in 100 milliseconds and it executes in 15. First off, it'll actually measure that and tell me, hey, you're only using, in that case, 15% of the allocated time window. Is that
Right, right. So you can do
okay?
things like that, and even more importantly, you can see if you went past that, if you took more than
Yeah.
100 milliseconds to run. So you'll get an indicator out that says, "Hey, that last iteration finished late." That's what we call it. So, and you might
So
take some action based on that. It's up to you.
okay. So I actually think that in my years of visiting with customers and seeing their applications, I would safely state that all of the coolest LabVIEW applications were using real time. CERN is one of my more memorable examples that we can talk about. And as is often the case with these systems, you actually see a mix of execution targets. You see a lot of real time. You also see some FPGA and even some host-based machines all talking to each other in pursuit of best performance. What are some guidelines for what belongs on the FPGA versus on real time versus on a host PC?
Yeah, that's a good question. So I think kind of my rule of thumb, which may not be definitive, but kind of what we've done before is if you're okay with milliseconds, tens of milliseconds of jitter or latency, then you can probably run something on the desktop just fine. If it's less than that, then you probably want to use an RT target. And if it's less than that tens of microseconds we were talking about earlier, that's where you probably need to move something into an FPGA where it can get down into nanoseconds of jitter.
That makes sense. And yeah, some of those applications like CERN actually controlling the Hadron Collider and the collimators, right, the magnets to actually control that beam. They were using FPGAs and real time for that control loop. Um, so related, when you have these complex topologies, you end up with a lot of different communication mechanisms to talk between these targets, which I believe has some can have significant implications for the performance and determinism of each target. What are your go-to recommendations for communication? Let's start with between the host and the real-time controller.
Yeah, so there's really a lot of different ways of doing that. Shared variables are a nice, convenient way to communicate from host to target. There's also network streams, like if you're streaming larger amounts of data. Those aren't always the best for determinism, but so you can also do things like use UDP, where you don't have handshaking happening like you would in TCP. So it kind of depends on the application as far as like your tolerance for, losing data or determinism impact, things like that.
So you mentioned shared variables off the bat. I think we'll put that in the ease of use column, but increasingly, I think as people are concerned about not just performance but also security, there are better solutions. So UDP is one. I guess perhaps even RESTful API. What about like MQTT? I'm just curious if that's a popular solution.
Yeah, I think things like MQTT, WebSocket, things like that have their place. Again, maybe not the best for determinism. But again, if you're kind of designing it so that you have the kind of deterministic and non-deterministic areas of your application kind of separated from each other, then that can all be made to work.
Well, and this highlights a key point that I think Greg and I talked a lot about, which is the the simplicity of having separate threads in your execution process. So I think to emphasize your point, do your network communication, whatever you prefer to do, but keep that separate from the critical or safety critical aspects of your system that need to be deterministic. And in LabVIEW, it's as simple as two separate loops. Okay, so what about RT to FPGA communication?
Yeah, so you can use the FPGA nodes and also DMA, I believe. I'm not the world's greatest FPGA expert. Typically stay more on the RT side, but yeah, those are the main ways you're going to communicate from RT to FPGA.
Okay, so and we will have an episode coming up about the underpinnings of LabVIEW FPGA. But Ken, one thing you are an expert on is I believe you were one of the individuals that worked on what would become the Raspberry Pi BeagleBone Black IP, which was derived from your work on real time. And I know I've used that, and I know it was a fan favorite. What what did you do? What exactly is that toolkit, and how similar is it to just the RT module itself?
Yeah. Good question. So yeah, that was just kind of a fun brainchild of a few of us that we'd been working on RT, and we started thinking about, hey, it seems like we should be able to run this stuff on a Raspberry Pi. It's a similar enough device. It's running Linux, and a lot of us are fans of Raspberry Pis and Arduinos as well. And so we were kind of like, how can we make this work? So yeah, really, what we cooked up was basically it's kind of like a lightweight version of the real-time module that's designed to run on devices like the Raspberry Pi. So yeah, even though we don't really say real time because we don't worry as much about tuning it for determinism because it's kind of a hobby electronics device. It under the hood, it really is mostly the same as a lot of our RT targets.
So as new Raspberry Pis have come out, I think the latest one is Raspberry Pi 5, and I know there's a bunch of other single board targets. Is the code that we generate, again, presumably happening at the I guess after defer, it becomes target specific.
Mhm.
Is that unique to every target, or can I take that toolkit? I think at the time Raspberry Pi 3 would have been the latest and greatest. Can I target a Raspberry Pi 5 with it, or does that work?
Yeah, no, it's mostly the same from LabVIEW's perspective. So we're basically generating 32-bit ARM code, and it really is the same as what we would generate for one of our ARM targets, like a C-RIO, a compact RIO device.
Okay.
So, and we have had to make some tweaks here and there for like later generations of Raspberry Pi, but not in the compiler. The compiled code is mainly just worked as is, which has been
So,
nice.
so is the work you're having to do the targeting of it, like actually deploying the code to it?
Yeah, it's there's been a few details, like a lot of it is how you install the LabVIEW runtime on one of
Uh,
these targets. A lot of times the Raspberry Pi folks will make updates and changes to the operating system, and they'll just slightly change things in a way that requires us to kind of do things in a slightly different way as well. Um, that's the most common thing that we run into.
Okay.
Like most recently, I think we were getting the Raspberry Pi 5 to work, and they had kind of changed the some of the low level like driver interfaces to the digital I/O, and so it our implementation broke. So we had to kind of update how we talk to the digital I/O on a Raspberry Pi.
So how do I get, since you mentioned that you've done work for Raspberry Pi 5, how do I get my hands on that? Is that in the latest version of the toolkit?
Yeah, yeah. So
Awesome.
see, I believe 2024 Q3 had support
The community
for
edition specifically, right?
Community Edition. Yes,
Awesome.
correct. Had support for Raspberry Pi 5. Um, and so we will, and onwards too, in future versions, we'll keep support going for that.
Awesome. Yeah, that's a popular toolkit amongst enthusiasts. Something I know I've used for home projects myself. All right. Well, I think that covers most of the key points about. Oh, wait. Actually, I do want to ask one of the key questions. You mentioned the runtime engine earlier, and I'm just curious to understand how different is the runtime engine on a real-time target versus Windows?
Yeah, it's really, really similar. It's actually even the same code base, but we build it a little differently. So the main thing is we strip out all the kind of IDE or ADE portions that you would use to develop code. So the only thing it can do is run code. It can't, edit or compile code.
And there's no UI, right? So I assume that is
Right.
all removed.
Well, some targets do have some x64 targets are actually capable of having a front panel, but you can't edit
Uh,
the code. So you can run the code and view the front panel on an attached monitor, uh, but you can't actually like edit the block diagram.
okay.
So even some of the UI elements are there. It's just mainly the editor part of LabVIEW is removed.
Okay. All right. Well, anyway, Ken, hey, thanks for all the work you do on LabVIEW Real Time and on the community toolkit for Raspberry Pi. Um, Curious, is BeagleBone Black still supported in the latest release?
Yeah, still
Yeah.
supported.
Awesome. And Arduino as well?
Yep, sure is.
Cool. All right. Well, thank you so much, and thanks for your time. And if you're interested in more videos like these and some of the upcoming episodes about things like FPGA, be sure to like and subscribe. And if you have a question for Ken and want to learn more about any of the things he said, be sure to leave a question in the comments below, and we'll get back to you as soon as we can. Thanks, Ken.
No problem. Thank you.